Jai Hind everyone. My name is Pardeep and I am working as an assistant professor in IT department in Ajay Kumar Garg Engineering College, Ghaziabad. Okay. So today we will discuss about the subject Tafl, Theory of Automata and Formal Languages. Okay. And the subject code is KCS 402. So our today's topic is minimization of DFA. DFA stands for Deterministic Finite Automata. Today we will discuss about the subject Tafl, Theory of. Okay, so let's start. Now, what is minimization of DFA? So, the process of reducing a given DFA to its minimal form is called as minimization of DFA. What it means? We minimize the DFA. In what sense? We minimize the number of state. Means, so there is one DFA, okay, and we perform the minimization on it. We perform the minimization on it. Okay, so suppose it contain n number of state. Okay, it contain n number of state. Okay, we perform the minimization and the result is minimized DFA. Result is minimized DFA. And suppose this minimized DFA contain m number of state. Okay, this minimized DFA contain m number of state. So what is the relation between m and n? So the relation between m and n, that n is greater than equal to m. Okay, so means after minimization the number of states will be reduced. Okay, the DFA in its minimal form is called a minimal DFA. Okay, and it contains the minimum number of state. It contains the minimum number of state. Fine. Okay. Now, so how to minimize DFA? So there are two popular methods for minimizing a DFA. First method is equivalence theorem. Okay, equivalence class theorem, and the second method is MyHill Nerode Theorem. We can also call as table filling method. Okay, table filling method. There are two methods. We will discuss one by one. So let's see minimization of DFA using the equivalence class. Using the equivalence class. In the equivalence class method, we eliminate all the dead state and inaccessible state. What it means? That there are two types of state. Our first step is we eliminate all the dead state and inaccessible state. What it means? Dead state are those non-final state which transit to itself for all input symbol in sigma are known as dead state. So suppose there is one state Q node, okay, and there is one final state QF. We'll denote the final state by two concentric circle. So suppose on A it goes to final state and on B it goes to some state Q1. Okay, and there is on A and B. Okay, so there are two state. One is inaccessible state and one is dead state. So let's see one by one. Next is inaccessible state. All those states which can never be reached from the initial state are known as inaccessible state. Okay, so that this Q1 state for all the transition A and B transit to itself only for all the input. So this state is dead state. This state is dead state. Okay, for all the input it will reach only itself only. Okay, and what are the inaccessible state? That we can't reach to that state from the initial state. What it means, suppose there is one state Q2, okay, and suppose on A it goes to QF and on B it goes to Q2 itself. So from Q node we can't reach to Q2 state, so it is inaccessible state. Okay, so this is inaccessible state. This state is, we can't access this state, so this is inaccessible state. Okay, so all non-final state, okay, which transit to itself for all the input symbol. And what is inaccessible state? All those state which can never be reached from the initial state. From the initial state is known as inaccessible state. The example is shown here. Next step is in the minimization of DFA for the equivalence theorem, that draw a state transition diagram table for the given DFA. We draw the transition table for the given DFA, and the third step is now start applying equivalence theorem. Okay, how we can apply? Take a counter variable k and initialize it with a value 0 and divide Q, what is Q? Set of state, into two set such that one set contain all the non-final states and other set contain all the final state. This partition is called P node. What it means? Suppose there is set S, which is set of state. We divide this set into two set. Okay, suppose set S node and S1, and suppose set S node contain all the non-final state and set S1 contain all the final state, and this partition is known as P node. This partition is known as P node. Okay, next step is increment k by 1. Now find pk by partitioning the different set of pk minus 1. In each set of pk minus 1, consider all the possible pair of state within each set, and if two set are distinguishable, partition the set into two different set into pk. Okay, we will see with example how this will happen. Okay, now two set Q1 and Q2 are differentiable in partition pk for any input symbol A if delta Q1 on input A and delta Q2 on input A are in different set in partitioning pk minus 1. Repeat the step 4 until no change in partition occur. In other word, we can say pk equal to pk minus 1, then we will stop. All those state which belongs to same set are equivalent, and the equivalent state are merged to form a single state in minimal DFA. Okay, so the number of state in minimal DFA is number of set in pk. Okay, we will see with example. So let's see this example. Okay, first step is draw the transition table. Draw the transition table for this transition diagram of DFA. Okay, so there is state, okay, on there are input. Okay, now on state Q node, state on input A goes to state Q1 and Q node state on B goes to Q2. Now take state Q1 on A goes to Q1 itself and Q1 on B goes to Q3. So write it here. Now state Q2. Okay. Now Q2 on input A goes to state Q1 and Q2 on input B goes to Q2. Now take state Q3. Q3 on A goes to Q1 and Q3 on input B goes to state Q4. Now let's check on state Q4. Q4 on A goes to state Q1 and Q4 on B goes to Q2. So this is the transition table for the given DFA. Now we find the equivalence class. Okay, so let's write equivalence class P node. Okay, 0 equivalence class P node. Fine, P node. Now okay, this state Q4 is final, so I mark it as star. Okay, star. This is the final state. Right. Now we divide this set of state into two sets. One set contain the final state and the other set contain the non-final state. So Q node is non-final state, Q1 is non-final state, Q2 is also non-final state, Q3 is non-final state, and the other set is Q4, which is final state. Now find the one equivalence class P1. Okay, now check Q node and Q1. Okay, Q node and Q1. Q node only goes to Q1 and Q1 only goes to Q1. So Q1 and Q2 belongs to same set? Yes, because they are the same state. So they belongs to same set. So Q node and Q1 comes together. Now similarly compare Q node and Q2 or Q1 and Q2, because Q node and Q2 are in the same set. So Q1 and Q2. So Q1 and Q1 both are same state. So they belongs to same set. Q3 and Q2. Q2 and Q3, they are in the same set. So this Q2 will come together with Q1. So Q node, Q1, Q2 will come together. Now compare this Q2 and Q3. Either you can compare with Q node or Q1. Since Q1 and Q2 are in the same set, so you can compare with any one of them. So Q2 and Q3, Q1 and Q3 both are in the Q1 and Q2 means they are the same state, means they are in the same set. Okay. Similarly Q2 and Q4. Q2 in set S node in set 1 see here, Q2 in set 1 and Q4 in set 2. So these are in different set, so we partition them. Okay, so we partition them, so we separate them and write Q3 as separate state. Okay, and Q4 is as it is. Okay, now find the two equivalence class. Okay, now see the equivalence class 2. Okay, now compare Q node and Q1, Q node and Q1, Q node and Q1, Q1 and Q1 same state, so it is in the same set, so Q node and Q1 comes together. Okay, see, no, just wait, we see the both state. Okay, fine, Q1 and Q node and Q1 is the same state, they belongs to same set. Now see Q2 and Q3, I am seeing the Q node and Q1 comes together or not. So see Q2 and Q3. Now see Q2 in set 1 and Q3 in set 2. So they are in the different set. So we partition Q2 and from. So we partition this Q2 and Q node and Q2, Q node and Q1. So we partition them. Q1. Now see Q1 and Q2, Q1 and Q2, Q1 and Q2, Q1 in the same set and Q2 and Q3. See, this is also in the different set. Okay, so we can see that Q node and Q1. Okay, fine, Q node and Q1 same set or different set. Okay, this Q1 this Q node and Q1 in the same set and Q2 and Q3 are in the different set. So we partition Q node and Q1. Now see the Q1 and Q2, Q1 and Q2, Q1 in the same set and Q2 and Q3 are in the different set. So Q2 is separate. Now compare Q node and Q2, Q node and Q2, take the different color, Q node and Q2. Now Q1 and Q1 are the same state. Okay, and Q2 and Q2 are the same state. Okay, so they belongs to same set. So Q1 and Q2 comes together, Q node and Q2 comes together, Q node, take the different color, Q node and Q2 comes together and Q1 is separate state, Q3, next is Q4. Now find the third equivalence class. Now compare Q node and Q2, Q node and Q2, Q1 same state, so they belongs to same set. Q2 and Q2, this is also same state, so they belongs to same set. So which is equivalent to Q node and Q2 Q1, Q3 and Q4. See here, this P2 and P3 are equivalent, so we must stop here. Okay. Now from the minimized DFA, now combine this Q node and Q2 are equivalent state. So we combine Q node and Q2. So there are 4 states now. Q node and Q2, one state. Q1 is second state. Q3 is third state. Q4 is fourth state. Q4 is fourth state. Now Q4 is the final. Q4 is the final state. So write in concentric circle form, and Q node is the initial state. Just write it. Now Q node on A goes to Q1. Q node on B goes to Q2. So it goes to Q2 only. Now see Q2 on A goes to Q1, Q2 on B goes to Q2 only. Now see the Q1 state. Q1 on A goes to Q1 and Q1 on B goes to Q3. Okay. Q2 is done. Okay. Q2 on A goes to Q1, Q2 on B goes to Q2. Okay. Next is the Q3. Q3 on A goes to Q1, Q3 on B goes to Q4. Okay. Now see next Q4. Q4 on A goes to Q1 and Q4 on B goes to Q2. Q4 on B goes to Q2. So this is the minimized DFA. So here the number of states are 4 and here the number of states are 5. Okay. So this is the minimized DFA. This DFA is the minimized DFA. Okay. This DFA is the minimized DFA. Fine. Okay. Next, see the next example. Okay. Now the given DFA is this one. Now here, first of all, we see is there any dead state or inaccessible state. So see here from Q node we can go to Q1, from Q1 we go to Q2. So Q1 and Q2 are accessible. Now see, is Q3 is accessible or not? From Q node there is no path towards the Q3. So this Q3 is inaccessible state. So we eliminate this state. So we eliminate this state. Now consider these 3 states only and form the transition table. So there is state input A and B. These are the input. Okay. On state Q1 we can go to Q1. On state Q node, on input A we can go to Q1. On input B, on state Q node we can go to state Q node only. Okay. Now see next state Q1. On state Q1, on input A we can go to state Q2. On Q1, on input B we can go to state Q1. Now see the state Q2. on input A we can go to state Q1, on input B on state Q2 we can go to state Q2. Okay. So, this is the transition table. Now, we find the equivalence classes. So, first of all P node 0 equivalence class. Okay. Equivalence class 0. Now, say we partition the state into two sets. One set contain the final state and the second set contain the non-final state. Okay. So, one set is Q node and second set is final state. What are the final state? Q1 and Q2. So, we write Q1 and Q2 combinedly. Okay. So, this is 0 equivalence class. Now, let us see the 1 equivalence class. Equivalence class 1. So, Q node is only one state, so there is no need of partitioning. Now, let us see the Q1 and Q2. Q1 on input A goes to Q2, Q2 on input A goes to Q1. So, this Q1 and Q2 belongs to same set, set 2. Okay. Similarly, Q1 and Q2 belongs to same set, set Q2. So, it is same as Q1 and Q2. So, we see that P node is equal to P1. So, we must stop here, okay, because these two sets are equal. Okay. Now, this Q1 and Q2 state are equivalent. So, we combine them. So, there are only two states. One state is Q node, okay, which is initial state, and second state is Q1 comma Q2. Okay. So, on input A on state Q node we goes to state Q1, on input B on state Q node we goes to Q node itself, on input B we goes to on input itself. Q1 on input A goes to Q2, Q1 on input B goes to Q1. Similarly, Q2 on input A goes to Q1 and Q2 on input B goes to Q2 only. So, this is the final DFA. This is the final minimized DFA. So, here the number of state are, here the number of state are 2 and in this number of state are 4. Okay. So, this is minimized DFA, deterministic finite automata. This is minimized DFA. Okay. Let us see the third example. So, in this example, let us see, is there any inaccessible state? So, from Q node we can go to Q1 and from Q2 we can go to Q2 and from Q node we can go to Q1 to Q4 and from Q node to Q3. So, all 4 states are reachable, all 4 states are reachable. Okay. So, there is nothing to eliminate. So, construct the transition table for that. So, let us construct the transition table on input A and B, and there is one more column state. So, there are total 5 states: Q node, Q1, Q2, Q3 and Q4. Okay, there are 4 states. Q node on input, okay, there are 0 and 1 instead of A and B. So we can write it 0 and 1. Okay. Q node on input 0 go to Q1, Q node on input 1 go to Q3. Now Q1 on input 0 goes to Q2, at state Q1 on input 1 goes to Q4. Now Q2 on 0 goes to Q1, Q2 on 1 goes to Q4, Q3 on 0 goes to Q2, Q3 on 1 goes to Q4, Q4 on 0 goes to Q4, Q4 on 1 goes to Q4. So this is the transition table. Now let's find the equivalence classes. Okay, so find the zero equivalence class. We denote with P0. In zero equivalence class, we divide the state into two sets. The one set contain the non-final state and the second set contain the final state. So there is Q node, Q1, Q2 and Q3. These are the non-final state set. Okay, non-final state set, and Q4 is the final state. So just write star to identify that Q4 is the final state. This Q4 is the final state. Okay. Okay. Now find the one equivalence class. Now see Q node and Q1, Q node and Q1. So Q1 and Q2, Q3 and Q4. Q1 Q2 belongs to same set. Q3 Q4, Q3 belongs to set 1 and Q4 belongs to set 2. So we must partition them. So Q node is separated from Q1. Now check Q node and Q2, Q node and Q2. Okay, Q node and Q2. So Q1 same state, so they must belong to same set. Q3 and Q4, they are the different set. Q3 and Q4, they are the different set. So we must separate Q2 also. Okay, we must separate Q2 also. Okay, now check Q1, Q2, Q3. So take different color, Q node and Q3. Q1, Q2 same set, Q3, Q4 different set. Okay, so this is also separated. Okay, so Q node, Q1, Q3, all these are separated. Okay, now see Q1 and Q2. See Q1 and Q2, Q1, Q2. Q1, Q2 belongs to same set, Q4, Q4. So these two states must be combined. See Q2, Q3, Q2, Q3, Q1, Q2 same set, Q4, Q4 same set. So these three states are combined. So we rewrite it again, Q1, Q2, Q3. These states must be combined. Q1, Q2, Q3, and the third set is Q4. Now contain two equivalence class, Q node. Now see again Q1 and Q2, Q1 and Q2, Q2, Q1 same set, Q4, Q4 same set. So these must come together. Q2, Q3, Q1, Q2 they belongs to same set, Q4, Q4 same set. So this Q1, Q2, Q3 they belongs to same set and Q4. Now see, P1 is equal to P2, so we must stop here, and these three states are equivalent. These three states are equivalent, so we must combine all these states, Q1, Q2 and Q3. We combine these three states. So just rewrite it here. So one state is Q node, second state is Q1, Q2, Q3, and the fourth state is final state, which is Q4. Okay. Q node is the initial state. On input 0, it goes to Q1. On state 1, it goes to state Q3. Okay. Now Q1, Q2, Q3. Q1 on 0 goes to Q2. Q1 on 1 goes to Q4. Now see, Q2 on 0 goes to Q1, on 1 goes to Q4. Q3 on 0 goes to Q2, on 1 goes to Q4. Q4 on 0 and 1 goes to Q4 only. So this is the minimized DFA. This is the minimized DFA. And how many states it will contain? It will contain 3 states. Okay. So here number of states are 3, and here the number of states are 5. So 2 states are reduced. So this is how we can minimize the DFA and form the minimal DFA. Okay. So let's see the next theorem, minimization of DFA using MyHill Nerode theorem. So MyHill theorem can be used to convert a DFA to its equivalent DFA with minimum number of states. With minimum number of states. The method of minimization is also known as table filling method. So MyHill theorem is also known as table filling method. In this method, we create the all pair of states involved in the given DFA and mark all the pair QA and QB such that QA is the final state and QB is the non-final state. What it means? We make all the pair, okay, and we tick mark them such that first state is, one is non-final state and second is final state. NF stand for non-final, F stand for final. Okay. It can be one final and non-final. The order does not matter. So if there is an unmarked pair Q and QB such that delta of QAX and delta of QBX is marked, then mark QAB. Okay. Here X is input symbol and repeat this step until no more marking can be made, and combine all the unmarked pair and make them a single state in minimized DFA. So what is the meaning of point 3? So if there is any unmarked pair QA and QB, okay, and there is one transition, delta of QA on some input X and delta of QB on some input X, it gives some state, okay, Q dash, Q double dash, and this state is marked. This state is marked in the table. Then we mark this QA and QB also. So let's see with the help of example how we can do that. Okay. Now the example is shown here. So this is the given DFA, and this DFA is minimal or not, we can't say. Okay. So first of all, let's see, is there any unreachable state or any dead state. Okay. So QA is the initial state. From A we can go to B, so B is reachable. From B we can go to D, so D is also reachable. From D we can go to E is also reachable. From A we can go to C, so C is also reachable. So there is, all the state are reachable. So let's see, is there any dead state. So dead state is that state for all the input it goes to, it transit to itself only. So A is also not dead state, because on 0 it goes to B, on 1 it goes to D. So D is also not dead state, because on 0 goes to B, 1 goes to E. E on 0 goes to B, on 1 goes to C. C on 0 goes to B, and on 1 it goes to C itself. Okay. So there is no dead state and no unreachable state. Okay. So let's write the table for that. So how many states are there? So there are total 5 states. So we make the table for this state. So we make a matrix of 6 by 6. Why 6 by 6? Because one row, one column are to denote the states. So there is state A, B, C, D and E. There is state A, B, C, D and E. Okay, we fill this table, okay, and combine, find out which two states are equivalent. Since A is equivalent to A, so we mark it as cross, so there is no need. C is to C is equivalent, D is D equivalent, E and E are equivalent. So B and AB are equivalent. Either we check on the upper right triangular matrix and lower triangular matrix. So let's see, check the lower triangular matrix. So we mark all these cross, no need to check on the upper triangular. Either you can check upper triangle or lower triangle. Okay. So let's check on the lower triangular. Okay. Now we mark all the state such that one state is final and other state is final. See here, which state is final here? State E is final here. So state E is final and all other are non-final. So this complete row will be marked. So E and A is non-final, E is final, B is non-final, E is final, C is non-final, E is final, D is non-final, E is final. All these are marked. Okay. Now what are the other pair which are not marked? AB, AC, BC, AD, BD and CD. So make all the pairs and see all the transition for that. So what are all the pair which are not marked? AB, okay, AB, A on 0, B on 0, where it goes? A on 0 it goes to state B, and B on 0 it goes to state B itself. Okay. Next, A on 1 it goes to C, and B on 1 it goes to D. Okay. Second unmarked pair is just write all these transition first, okay, and then we will check. Just write all the transition, okay, to differentiate, okay. Now second unmarked pair is AB, next is AC. Let's see the AC. A on input 0 and C on 0. A on 0 it goes to B, and C on 0 it goes to B, okay. Second is A on 1 and C on 1. A on 1 it goes to C, C on 1 it goes to C itself, okay. Next unmarked pair is AB, AC, next is AD. A on 0, D on 0. A on input 0 it goes to state B, D on 0 it goes to state B, okay. Next A on 1, A on 1 it goes to state C, B on 1, B on 1 it goes to state D, okay. So this is one pair, second, third, okay. Next is okay, BC, this is unmarked, okay. So make the pair BC, okay. BC, B on 0, C on 0. B on 0 it goes to B, C on 0 it goes to B, C on 1, B on 1, C on 1 it goes to C, B on 1 it goes to D. Next is BD. Let's see the pair BD. B on 0, D on 0, B it goes to B, and D on 0 it goes to B only. Similarly B on 1, B on 1 it goes to D, and D on 1, D on 1 it goes to E, okay. Next state is CD. Next pair is CD. C on 0, D on 0. C on input 0 it goes to B, D on input 0 it goes to B. Next C on 1 and D on 1. C on 1 it will go to C, and D on 1 it will go to E, okay. These are the pairs. Now check these pair are marked or not. BB is marked, not marked, okay. BB is marked, not marked, okay. This BB is also not marked, this BB is not marked, okay. Anyone. Now see, CD is marked, not marked, okay. CC, CD is not marked. Now see EC, EC is marked, EC is marked here, so we mark CD, so CD will be marked here, CD will be marked here, okay. Now see DE, CD, where other CD is marked. Now CD is marked, so now we mark BC also. Since CD is marked, so we mark BC also. Now CD is marked, we mark AD also, we mark A and D. Now see, DE is mark, yes, DE, okay, AC, this is A on 1, it goes to C, C on 1, it goes to C. This is not mark, okay. Now see the B and D, B on 0 it goes to B, D on 0 it goes to B. This is not mark, B on 1 D, D on 1 E, D E it is mark, so this will mark here, okay. Similarly AC, this will be marked. Now this state is vacant, so we combine this A and C. So combine this state A and B, this state will be combined A, B, C, D and E. So these are the 4 states. These 4 states are combined and we form the minimal DFA, okay, using this transition diagram, okay. Thank you.